Hello all. So we're together again in a ring charge problem. This time we're going to be calculating the electric potential due to this ring charge, again at its center axis at a distance x from the center. And this charge Q is uniformly distributed across the length of the ring. So let's get started again by defining a coordinate system so we can properly define our limits on that coordinate system. So let's put an x, y, and z coordinate system at the center of the ring so that the YZ plane is the plane of the ring and x-axis is perpendicular to the plane of the ring. It's the center axis of the ring. So we're again going to have a number of steps to be able to calculate electric potential due to a charge distribution utilizing the electric potential of a point charge K Q over R. But we are going to modify this. We're going to pick a small dq on the charge distribution and define the small potential created by that small charge. So hence, our first step is to pick a random dq on our charge distribution, rewrite it in terms of charge distribution, lambda, sigma, rho, rewrite our dv, and dv has this r in it, which we have to define. And then finally, we're ready to integrate after defining our limits, which determine where the charge lies on our coordinate system. So again, let's have a summary of steps down below to guide us through the exercise. All right, so we're going to use a little dq again on the charge distribution. So let's pick this dq again. And we're going to use line charge distribution to define our dq. Line charge distribution of the ring is total charge Q distributed across the circumference of the circle, which is 2 pi r. We have a dl again, and this dl will be determined by a small angle d phi, which is an angle on the YZ plane. So we have Q over 2 pi r. Small length dl is an arc length, so it's the radius of curvature times a small angle d phi. All right. Hence, dq can be written as q over 2 pi d phi. All right, there's our dq. Now we can move on to calculating a d phi using this dq. So dv equals k Q over 2 pi r d phi. So now we have to define this r. So we're calculating electric potential at point P due to this charge dq. Hence, r is the distance between dq and point P. This distance. Again, r can be described in this triangle. Since this side of the triangle is on the YZ plane and x-axis is always perpendicular to the YZ plane, this is a right angle. So this is a right angular triangle with sides x and r can be rewritten as square root of x squared plus r squared. Hence, we can rewrite dv as kq d phi over 2 pi square root of x squared plus capital R squared. Beautiful. Now that we have a dv defined, we can move on to the last two steps of defining the limits and integrating. How do we define the limits? Where we have an integration over the variable phi, and we have to determine our limits looking at the angle phi. We have to be scanning all of our charge at this point. Here phi equals 0 degrees, and it increases as you go around the ring, 90 degrees, 180 degrees, which is pi, all the way back to phi equals 2 pi. So we have from 0 to 2 pi as our limits. So V is KQ over, these are all the constants in the integral, 2 pi x squared plus r squared integral d phi from 0 to 2 pi. Integral of d phi is just phi from 0 to 2 pi, which is 2 pi. So electric potential due to a ring charge at a distance x from the center axis is kq over 2 pi x squared plus capital R squared times 2 pi, and 2 pi's will cancel off, giving us a result of kq over square root of x squared plus r squared, and this is our result. As you can see, it depends on distance x, charge q, and radius of the ring, and as you go closer to the ring, x becomes 0, hence the potential is going to be highest at this point, and the answer will be kq over r, just like a point charges. So at the center of the ring, our potential is k capital Q over r. All right, here is our result, guys, and I will see you at the next question.